Okay, so we can start our next lecture. This is lecture 2. So we will talk about continuous time filters for today's lecture. So let's go through it. So lecture 01 video and slides are available, so you can check slide and video from my courses platform. So like PDF file, slide, and video is uploaded to YouTube. You can check it. And including this video will be also other lecture videos will be uploaded. So questions. So you're again, we are welcome to ask questions at any time during the lecture, and you can also post questions. You press them. So scan the QR codes. The access code will be different for every single lecture, so you cannot use the same access code. Selected questions will be answered in the next lecture. So thank you for asking questions. So we received one question in lecture 1. So the question was, why not take the quiz after the lecture it is connected to, rather than a week later? This is a good point. And my answer would be, the quiz is scheduled 1 week later to give extra time for study, and it will be designed to be slightly more challenging than just immediate post-lecture quiz. So you will not like always need it, but it will be at least helpful to have 1 week. Okay, so for the CAD exercise 1 exercise, there are some updates. So 2 instructions have been added. The first one is how to change the keyboard layout in VMware. When you access to VMware, it will be, by default, it will be set to finish keyboard layout, but if you are an international student, it will be helpful to check it. How to set Spectre as the default simulation engine. So it will be also helpful for going through CAD exercise 2. And for CAD exercise 2, you will work on CAD exercise 2 after today's lecture 02. And please submit a report answering the questions specified in the CAD exercise 2 instructions. And the deadline is almost 2 weeks later, Tuesday, 27 January 2026, and 11:59 p.m. Helsinki time. And the late submissions will be graded with 0.5x score multiplier. This means that if you just perfectly write the report with a perfect score, you will get only 50% of the original score. But this is because we will go through the solutions and how to design the CAD exercise examples in 28th January. So it will be much more easier after submission deadline to submit or write a report. So it is regarding the fair assessment. Okay, so what are we going to run in lecture 02, intended learning outcomes? So we will review some passive RC filter fundamentals. We will go through theory and feedback and Laplace analysis of first-order systems. And we will have a live demonstration. So I will show how to simulate very simply pole zero simulation in Cadence Virtuoso. And about analysis, we will go through limitations of passive filters. What kind of limitations are there? So before we jumping into our main topic today, we will first go through the remained things that we couldn't finalize in previous lecture 01. And we will go through RC low-pass filter. It's just first order RC low-pass filter, second order RC low-pass filter. Those are quite easy. You might think, oh, this is, why do I have to learn about this again? But there are some interesting vectors that we need to think about. They'll be helpful for the next lectures to analyze or to study about more complicated circuits. So we will go through feedback theory and Laplace transform and pole zero simulation. About second order RC low pass filter, loading effects, and limitations will be discussed. And we will go through feedback theory and Laplace transform in the next lecture of second order RC low pass filter. Okay, then let's go to sampling theory. So you can again go to scan the QR code or go to this website for aliasing demo. And let's see. Okay. And right. So everyone access to this demo. Okay, I believe so. So the questions were, under what condition does the clock appear to rotate at rotation per second? This is clock speed equal to 1. For the first question we went through, right, clockwise, even though RPS is not equal to 1 rather than 1, but it can be the same. About the counterclockwise with the same speed, the magnitude. And the counterclockwise while alternating between 2 points. And do we understand why? This was the question. So let's go through the second one. So counterclockwise. So when we plug in RPS equal to 1 to this phase equation that we derived in the lecture 1, then we can find out, okay, the left clock, let's say, I am setting left clock, and I am also controlling the right clock. And the left clock phase will be 2 pi n over FPS, frame per second. Frame per second, here it is a sampling frequency plus some offset, V0. About RPS equal to FPS minus 1, then we have this kind of equation, right? We can just plug this equation into RPS. So in this case, here, this part, as we have figured out in the previous lecture, this one goes to 1, and 1 times here, this vector goes to 2 pi n. And remember, 2 pi is just 360-degree rotation. So it has no effect in the end. So what we end up is negative 2 pi n over FPS plus V0. So those are our only difference here. The magnitude is the same for the clocking speed, but its opposite, its polarity is opposite. And according to Nyquist theorem, so let's check Nyquist theorem. So here we have a sampling frequency should be larger than 2 times f bandwidth, or the bandwidth of the signal must be less than Nyquist rate, which is half of sampling frequency. So in our case, this is our bandwidth, and this is a signal which is less than bandwidth, and FPS is a sampling frequency. So here we are violating Nyquist theorem, and because of this, the left clock and the right clock, it is rotating, rotating with the opposite direction with the same absolute velocity. So this is violating violating our, how do I say, the intuition, and this happens because of aliasing. So before we going to this part, we can check very simply here for easier visualization. I will use just 0.1, and here we have FPS equal to 60, right? So FPS minus 0.1 becomes 59.9. And then if we reset the clock, you can see that its clock speed is the magnitude is exactly same, but it has the opposite polarity for the traveling direction. And we can also see that its cosine phi is exactly same, and the sine phi also magnitude-wise is the same, but it has the opposite polarity. So negative 1 multiplied each other is the other one. This means that for the cosine phi, the x-axis value is the same, right? Here, x-axis. But the y-axis, it has the opposite flipping polarity. So, and let's check this frame-wise diagram. For the frame per second 60, which is our case, FPS 60, then our rotation per second equal to 1, it has frames like this. And for the rotation per second equal to 59, it has also frames like this. In this case, the apparent speed, which is a rotation per second, is equal to 1 in terms of magnitude, as we have checked. So it is indeed indistinguishable from RPS equal to -1 because it looks like it is traveling the other direction, but with having the same magnitude. So this is not true speed that we want to observe. So this happens because of aliasing. And when we increase the sampling speed twice to FPS equal to 120, then there is an interesting phenomenon happening. So RPS equal to 59, now it goes to clockwise speed, clockwise direction. It was traveling to counterclockwise, but we just increased the sampling rate, and it changes, for the traveling direction. So now clock rotates in the faster speed. This is also faster because previously it was rotating with a magnitude of equal to RPS equal to 1. It doesn't look like RPS equal to 1, not anymore. So direction is inconsistent and depends on our sampling rate speed. And this happens because of aliasing. When we look into the same RPS equal to 59, but with different speed, then we can more figure out easily. So we have frame equal to 1, frame equal to 2, which corresponds to frame equal to 3 in FPS equal to 120 case. Then we can figure out, okay, there is something missing piece here for the even numbers of frame numbers. So now clock rotates in faster speed again, and direction is inconsistent, and it depends on frame per second. So as we checked, when aliasing happens, then this is the case of RPS equal to 1, RPS equal to 59. So RPS equal to 59 is indistinguishable from RPS equal to -1. When we speed up, then there is something interesting happening here, right? So because of aliasing, the signal became faster at higher frame per second. It's counterintuitive. So when we take a motion with, for example, a camera with a video recording, when we increase the speed of the sampling, then it should look like more slow motion frames. But in our case, it became faster compared to this. And then it has a kind of these slow envelopes are detected, right? Which is corresponding to the RPS equal to 1. This is because of the earlier equation that we derived, this term. This is representing the envelope. Okay, so the third question is counterclockwise while alternating between 2 points. So did you figure out which is the condition? Was there anybody who couldn't figure out this one by playing aliasing demo? So when we plug in RPS equal to 1, and when we plug in RPS equal to half FPS minus 1, which is still satisfying the Nyquist theorem in our case, but it is more close to Nyquist rate, which is called near Nyquist. Here, we have this term, FPS over 2. It goes to just half, and half times 2 pi n results in pi n. And we also, again, have a negative term here, pi n minus 2 pi n over FPS plus V0. This is the condition of base equation on the right side clock. So in Nyquist, according to Nyquist theorem, for the for the bandwidth, signal bandwidth must be less than Nyquist rate, FPS over 2. So in our case, RPS equal to FPS over 2 minus 1 is still satisfying the Nyquist theorem, but it's near Nyquist frequency. So there shouldn't be any aliasing. And let's check that. So in our case, we are having signal signal frequency as a 0.1, and our FPS is 60. So the half FPS becomes 30, and minus 0.1, it becomes 29.9. And when we reset the clock, then we can see that, right? So it's enveloped. The overall traveling on average speed looks like -1, but it has alternating two points, in very high frequency. So this is happening because of the equation that we derived here, pi n term, and the overall envelope, it becomes negative 2 pi n over FPS. So in terms of frame-wise, then we can find that, okay, this is very similar to our case when we set our FPS equal to 120 with RPS equal to 59 case earlier, right? So it has a high frequency switching. So even if its overall envelope looks like -1 RPS, but it is still distinguishable from RPS equal to -1. So there is no aliasing. And when we increase the frame rate, then it becomes 120. Then high frequency switching is still there. Now it has 4 points. 4 points are pointing out, and the direction is consistent, and it is independent on the sampling rate. So there is no aliasing. And in terms of different frame rate, then we can see that, okay, so this frame corresponds to the same frame, and this one corresponds to the same frame, and this one corresponds to the same frame. And we can see that its rotation direction is consistent no matter how fast we are taking the frame rate, as long as it satisfies Nyquist theorem. So this is the situation that we just have looked. For the cosine phi, it still has envelope right here. So this part, it becomes envelope. This part, right? So this is happening because of this negative 2 pi n over FPS term, and we have very high frequency switching. So it becomes pi n or 0. So pi n times 2, it becomes 2 pi n. So more precisely saying, it becomes like this. Pi or 0. Then when we increase the FPS, which is sampling rate, even more faster, then signal became slower at higher frame per second. So it is still within our intuition. However, its overall waveform looks like difficult to analyze in time domain. So we cannot easily see the same envelope of this term, right? 2 pi n over FPS. So this is the reason why we are studying frequency domain analysis. We cannot just analyze our time domain signals with bare eye without a frequency domain signal analysis method. So this is a key takeaway at frame per second is 60. So we have RPS equal to 1, 29, and 59. So all of them corresponding to input frequency to 1 Hertz, 29 Hertz, and 59 Hertz. And the math, it becomes for RPS equal to 1 case, the input frequency is much slower than the Nyquist rate. So it goes to safe condition to sample without any corruption, without any aliasing. The sample data is correct for 1 Hertz, and sample data is also correct for 29 Hertz with RPS equal to 29, because it is still within our Nyquist theorem condition. But for RPS equal to 59, it becomes, input frequency is even closer to the sampling rate. It's definitely higher than the Nyquist rate. That is violating our Nyquist theorem. So this it goes to undersampled condition, and this is incorrect for the sample data. So it is corrupted or ambiguous, let's say. So the Nyquist rate is a safety limit. It guarantees the sample, the signal is unique, and there are some advanced techniques when you do some research. For example, IEEE journal papers or conference papers, there are terms so-called undersampling. and it violates Nyquist's theorem, but it can be robust if used very, very carefully. So those are quite useful techniques for low power design of analog circuits, but it is out of scope for this course. If you are interested in, you can search. Okay, then we can go and we can move on to first order RC low pass filter, which is very, very easy case to analyze. So, so we have looked we have looked on this microphone interface in lecture 01, and we figured out, okay, we need a filter for anti-aliasing here, right? To filter out our noise component before it is aliased back to our baseband. But I might ask a simple question. Can we simply use an RC low-pass filter for this anti-aliasing filter? And maybe yes, or maybe no. And those are the main topics we will go through. Can we just simply use an RC low-pass filter without thinking too complicated things? So we will go to recap on filters. So during your bachelor course, maybe, then you probably have studied low-pass filter, high-pass filter, band-pass filter, and notch filter. It is also called band-stop filter. And for the low-pass filter, it filters out high-frequency components. And high-pass filter, it filters out the low-frequency one. And band-pass filter, we don't care other signal bands. We only care about the center frequency. And the notch filter is the opposite. We just want to filter out specific frequency band. So this is a recap of filters about first order low pass filter. It has a low pass filter block diagram like this, and it means that when we plug in our input voltage, it it outputs an output voltage that has a transfer function of low pass filter characteristic in frequency domain like this. This is a low pass filter building diagram. And for the transfer function, can you can you guess what will be the transfer function of this? Gary? 1 over
2 pi RC.
2 pi RC. So you just guessed what it will be the pole frequency. Yeah. Yes, good. Thank you. And that's true. You get it. So you didn't forget about bachelor level. Easy ones. But of course, I believe all of you can compute or analyze this transfer function and the pole frequency. Let's go through basic exercise as a recap. So we can easily derive this transfer function using voltage division principle, right? So we can have impedance here. For this part, it has CR, which is equal to R, right? For the resistor's impedance. For the capacitor's impedance, it becomes 1 over SC, remember? Or you also might learn this one as J omega C. For the voltage division principle, we can just simply divide our voltages. Then it becomes 1 over SC over R plus 1 over SC. Rearranging this same equation, then we finally get 1 over 1 plus SRC. This is a transfer function. So when we analyze this one, we can indeed have different point of views to analyze this kind of very, very simple circuit. We will have a look on intuitive analysis and feedback theory. And you might think, oh, where is feedback? There is no feedback in this RC circuit, but there is one feedback we can analyze that will be very, very useful for our future studies. And we will also think about the Laplace transform. So this is Laplace transformed format, but we will go a bit more deeper dive. and circuit simulation. We will go through it. Okay. For intuitive analysis, we can use this kind of intuitive analysis when you happen to meet very, very complicated circuit in later when you study or do some research. So we can think about extreme cases. When we just send this or make this S term, which is here, thinking about steady state condition, then it becomes to j omega. Such that when we take S equal to 0, it means that we are looking at just DC only. In our case, when we look at DC, then this impedance or capacitance becomes 1 over SC, right? Then when we take S equal to 0, then it goes to infinity. So what will be the infinity value of impedance in circuit analysis? Do you know how to analyze it? Open circuit, right? Thank you. It's open circuit. This is because when we think about, okay, let's first think about this one first. The magnitude of S becoming to infinity, which is the high frequency. Then it goes to 0 for high frequency. So 0 impedance means that we can think about this resistance. When we make this impedance value as a 0 ohm, then it just means that there is no resistance at all. So this is a short circuit, we call it, and the other case becomes open circuit. So this is an infinite impedance condition. Right. So when we take a look on the first one, DC case, then our situation end up this case R, and this port is disconnected at all. So we don't have any formulated current flowing terminal that is touching VDD or ground. So there should not any current flowing into this direction. So current equals to 0. So current can flow only if there is some ground terminal or VDD terminal that the current can sink into it. So assuming that current is equal to 0 and V out is connected to nowhere, that means open circuit as well. In our case, if the current is 0, then the voltage difference here, VR, also it becomes to 0. That means V out becomes V in. So in our case, H 0, it becomes to 1. Its gain is just 1. And we can easily figure out by plugging S equal to 0, then as transfer function, it becomes to 1. On the other hand, for the capacitor value like this, when we take S magnitude going to the infinity, then it becomes high frequency. That means it is just connected to ground, such that V out is always becoming to 0, no matter how big is V in. V in is very large, like this, very small. We don't care because V out is already connected to ground, so it's always 0. Then in our case, let's just simply not write like this. Then it goes to always 0. In our case, we can also analyze this one by plugging S magnitude becoming to infinity. Then it goes to just 1 over infinity. It goes to 0. So thinking of this kind of relationship, let's take a frequency and HS, right? For the DC, we have 1. For infinity frequency, we have 0 magnitude. Then it becomes like this. So this is a linear scale. When we take log scale, hs, then the log 0, it becomes to negative infinity. So it goes to like this. So it becomes a low pass filter. Yes. Okay. So now the chocolate here. Thank you. You can also share with your friends if you feel I'm not hungry at all. All right, so let's have a look on the feedback theory. Okay, so let me first clarify, why do we have to look at this very, very simple RC circuit using feedback theory? Is there any feedback? This is the question that I want to raise during this lecture 02. So we have transfer function like this. And remember, if you learned feedback theory or feedback fundamentals during your particular course, then this diagram, you might have seen it during your course or in textbook. We have input, and we have a negative feedback loop, assuming it. Then we have open loop gain component, and the feedback factor, which is a beta, and A open, which is the open loop gain, and we have an output like this. And the closed loop gain, it becomes A closed. It is A open loop gain over 1 plus beta times open loop gain. Here, beta times A open, which is open loop gain, it becomes the loop gain. So is there any feedback? My answer is, as I explained, yes, there is. There is a feedback that will be very, very helpful when we analyze more complicated circuits in later. A low-pass filter can be interpreted as a feedback system. And we analyze this kind of simple passive circuit as a feedback loop, not just because it's more difficult or hard, but because the same framework applies to complex active filters later. But in practice, circuit designers, analog circuit designers, do not describe this kind of RC low-pass filter as a feedback circuit. We call it this open loop circuit because there is no wired feedback loop, but we can analyze this kind of circuit with feedback theory. And as I explained, we call this component beta times open loop gain as a loop gain T. And for transfer function, we can maybe rewrite this transfer function by this format to mimic the same structure of closed loop gain equation. Then it becomes the open loop gain. Well, our open loop gain, it becomes to 1 over SRC when we assume this, because we have a numerator here, And when we set feedback factor, beta, as 1, then our loop gain becomes to T equal to 1 over SRC, which is same as open loop gain. So by making this kind of equation, or fractional factors, then okay, there are some similarities, right? Closed loop gain and the transfer function. So we can make this part, numerator part, open loop gain, and also the same factor of numerator, 1 over SRC, as the loop gain. So when we apply this, we can build this kind of building diagram, which is now it has a feedback factor, beta equal to 1, and now we have omega p over s. So we have one integrator, which is omega p over s. So integrator in Laplace domain, it becomes to some factor times 1 over s, and plus one feedback loop. So those are essential building blocks of a low-pass filter. So we need an integrator, we need a feedback loop to build a low-pass filter. So here we have omega p equal to 1 over RC. Now it has a dimension of angular frequency, so radian per second. And when we take this dimension into physically Hertz domain, then we have to multiply 1 over 2 pi, as you discussed. As you mentioned, thank you. So 1 over 2 pi RC, which is pole frequency in Hertz domain. So we call this kind of low-pass filter as actually lossy integrator compared to the ideal integrator, which is a lossless integrator. So here is a transfer function looks like this, 1 over s. This is predictable because we have transfer function of integrator here, omega p over s. When we plug in, as we did for intuitive analysis, for the DC, the s equal to 0, then it goes to infinity, right? For the ideal case. Then it just blows up when we go to DC. This is also very easily predictable. When we build the ideal integrator, then it will just accumulate inputs forever, accumulating. So it will just end up blowing it up. So it matches to our intuition. However, when we set, as we did intuitive analysis, when we set s equal to 0, then it becomes to, here in our case, transfer function equal to 1. Then we can, we can see this kind of flat band as a gain equal to 1, which is a 0 dB in our case. So we call this integrator as a lossy integrator because its transfer function at DC doesn't go to infinity. So it kind of, there is a loss, but we call it as a lossy integrator, which is equivalent to first order low pass filter. But where is the feedback loop in an RC circuit? Can you guess? Where is the feedback loop? I mean, we've analyzed this kind of building block, but where is the feedback loop? Any idea? In this RC circuit. But there is no explicit, oh, you have? Capacitor. Can you charging and charging? Then what will happen? Can you explain more?
Well, I just thought maybe it charges.
It charges.
It keeps the like memory.
Memory.
Keeps that, and then it sends it back.
So, yeah, you are almost there. So send it back. Then what will happen? Then when we charge the capacitor. Almost there.
I don't.
Thank you. Thank you. Can you try?
Resistor act as will restrict the voltage.
Oh, sorry, can you repeat?
Resistor restrict the voltage drop, so might act as negative feedback.
Yes. So with the help of as a teammate, both of you figured out. Thank you. So yes, so there is feedback with the capacitor and the resistor. Of course, those are two components only. Let's have an analysis of what is happening here. As our colleagues have participated to the analysis, when we take the nodal analysis using just Kirchhoff's law, when we studied at bachelor level course, then we have IR equal to IC. Here, IR means the current flowing through the resistor, IR. And the current flowing through the capacitor, I should notate here as a small I case. We normally describe the current with the capital letter of I, saying it has a large signal. But when we take the small I case, it means that we are thinking of the small signals. This is very important when we analyze the circuit because any DC current cannot pass through the capacitor. But when we take the AC current, small signal, then it can pass through the capacitor. Anyway, let's take another analysis of this kind of circuit. Then, yeah, we can take V in minus V out over R. This is our current going through the resistor. When we think about the current going through the capacitor, V out over just impedance of the capacitor, then it becomes 1 over SC. And we can just a little bit more rearrange, then SC times V out. This is the equation. When we rearrange this equation, then you can get the same equation of transfer function, 1 over 1 plus SRC. There is an interesting thing. So as both of our colleagues helped out, there is kind of V out times SC part that is accumulating more and more and more, and it is actually negated to V in. So what is happening here? When we analyze this kind of feedback circuit, we can try the method of using feedback circuit. We can try the method of using assumption of, okay, let's take the assumption that the V out is increasing because of SC part, which is impedance. Then let's assume that V out is increasing. Let's say that, okay, our current is flowing into this capacitor. Then what is happening? Then the current going through this IR, it becomes less and less and less because its voltage difference is becoming less and less and less, V in minus V out. So it is acting as a negative feedback, right? It doesn't want V out to blow up. It doesn't want V out to go to always zero. So it is kind of a very good solution about regulating our V out by the means of negative feedback. So V out feeds back through resistor. And capacitor, which has an impedance value CC equal to 1 over SC, it implements an integrator in the S domain. So this is intuition about the feedback system. And when we go to Laplace transform, it will be more mathematical expressions involved. So again, recap on filters. Yeah, let's take a look on Laplace transform. So you might remember or recall is the equation of Laplace transform when you studied signals and systems course. This is called as a bilateral Laplace transform. Here, bilateral means that we are doing integral over negative infinity to positive infinity. And we have HT, it is impulse response. The output when we apply the unit impulse function. The unit impulse function, if you remember, this is the unit impulse function. And the area equal to 1. And e to the power of minus st and the integral over dt. This is a bilateral Laplace transform. When we think about this Laplace transform in unilateral domain, here unilateral means that we are taking integral over just 0 to positive infinity. So this happens because our physical system in our circuit analysis, our circuit world, those systems are causal. So causal LTI system. For the causal LTI system, its impulse response, HT, is always 0 for the negative time. So it means that it reacts only if we give the input. So let's assume that there is some non-zero value for the HT for negative t, such that, let's say, H minus 1 is some value. Then the impulse response, by definition, let's call this way. This is the impulse response. So when we analyze our impulse response with the negative 1 as an input, there is some output non-zero value. So this one actually have an area which is non-zero value only at t equals 0, such that we just give the input at the moment of t equals 0, but we get the output in the past. But this means the system is some kind of or somehow predicting the output, predicting the input, and it is generating output based on the future input. It doesn't make sense. So our physical systems are all causal. So we give some input, then it can react. So, okay. Let me remove all the annotations. And about this kind of family, this kind of Laplace transform family, when we take the inverse Laplace transform, then we can get, okay, e to the power of minus alpha t, ut, which is a Laplace transform, then it goes to 1 over alpha plus s. So for the region of convergence, so here region of convergence, I will talk about it in later slide. And region of convergence, it has a real value of s must be larger than minus alpha. So when we take Laplace transform of this format, 1 over alpha plus s, its inverse Laplace transform becomes some kind of exponential function times ut. Here ut is a step function. Very simple step function. 0 to 1. This is a step function. So for the region of convergence, ROC, it means that the condition on S such that the Laplace integral converges. So this part, this function should be decaying function. So otherwise, it will just blow up because we are doing integral over infinite value. Such that, let's assume that even if we are doing just integral over 1, then it goes to infinity. It doesn't converge. So when we multiply, our impulse response with some exponential, it must be decaying function. So that is the condition of ROC. So what kind of value of S can be applicable to make this component, ht times exponential, becoming to decaying function? That is a definition of ROC. So let's take a look at this, our RC low pass filter case. Then our transfer function looks like, in Laplace domain, it looks like 1 over 1 plus SRC. When we take the inverse Laplace transfer function, then we can just plug in this equation, right? R per equals to 1 over RC. Then it becomes, okay, we have e to the power of minus t over RC times ut. And the ROC becomes real value must be larger than negative 1 over RC. So by this condition, we say the system has a pole at the S equal to negative 1 over RC. And multiplying with this condition, the ROC, what it means that multiplying e to the power of t over RC with ht, it causes the Laplace integral to diverge. This is the boundary of the ROC. So we can easily think about this. So let's say we are taking the output and we are multiplying, this one, right? E to the power of st. E to the power of minus st. And when we take this one as e to the power of t over RC, such that the real value of S becoming to minus 1 over RC, then its output becomes to just ut, right? Here we have inverse Laplace transform, which is a time domain signal, multiplying this exponential and this exponential. Then it becomes to e to the power of 0, going to 1. Then it becomes ut. So in this case, our Laplace transform doesn't exist to convert. So this is by definition, we cannot define our Laplace transform. This is the meaning of boundary of the ROC. So here, on negative 4 here, S equal to minus 1 over RC, it doesn't mean that we are thinking of negative physical frequency. It just means that the condition, what is the tolerable multiplication factor that this system can stay as stable as it is. So in our case, again, as we derived, we call pole frequency 1 over RC, which is angular frequency, radian per second. And in Hertz domain, we call 1 over 2 pi RC. So it means that if we multiply, again, the system output by a growing exponential, here e to the power of omega p over t, omega p times t, sorry, then the system response blows up. It's a measure of system robustness. So when we draw this kind of pose in S domain, S plane, that we have x-axis as a sigma real value, which is the real part of our S, and we have a j omega axis, which is imaginary part of our S. Then we call this, okay, here we have pole, which has a 1/2 pi RC frequency, and we call, okay, our region of convergence is drawn in this domain. When we have a look on this, our Laplace, inverse Laplace transform again with the RC, and also thinking of unilateral Laplace transform equation, which is our case, causal LTI system. When we take sigma equal to positive value, some positive value for the real part, then this exponential case, this exponential factor, it becomes to less than 1 for the positive time, which means our causal system case. Then the multiplying or decaying exponential. This is a decaying exponential, right? Its magnitude is less than 1. Then in the integral, it is easier to converge. For this one, it is easier to converge. However, when we take the sigma negative 1, then we are actually multiplying the exponential with the growing exponential in the integral. It is more harder to converge. So we are kind of pushing some challenges or some weight to our system. And finally, when we think about our sigma equal to 0, then this exponential term becomes to 1. Then we can check whether the Laplace integral converges as is, without touching anything, without helping, without challenging it. So it is actually equivalent to the Fourier transform. When we take sigma equal to 0, then our S, which equal to sigma plus j omega, it just becomes to j omega when we take a sigma equals to 0. Then this part becomes to e to the power of j omega t, which you have probably seen during your signals and systems course as a Fourier transform. And this is a criterion to check system stability. And now we say the system is stable if regional convergence includes this j omega axis, this one. This one. Because this one is the case when we just multiply our exponential with the magnitude equal to 1, such that it is equivalent to Fourier transform. Okay, then let's go to pole zero simulation case. So here, which is a circuit simulation part that I prepared today. So okay. Oh, it looks challenging. It's challenging to control looking at this screen and my mouse. Anyway, so you will do this kind of CAD exercise through this course. So first, I would like to go through is we can set VDC here. No, sorry. Analog leaf, VDC. Then we have DC voltage equal to 0. This is DC, right? So for the shortcut to instantiate any components, we can just press I here. And we can go ground to connect here. And when you click this component and press Shift, then it automatically generates some wires. So this also is the true when we press Shift, space. Then we can automatically generate this kind of wire with label. Anyway, I'm going to rename this one. When you press T, then we can rename it. So let's call this one as a VSS. And when we want to save the schematic, then we can press Shift X. Okay. And when we press Shift M, then we can move this wire that is attached to this component. So if you just press only M, then it will follow your movement. So I don't want it. So I will go to Shift M and then doing Control R, and you can flip it over vertical direction. And when you do C, then you can do copy and paste. You can rename it as a VDD. But this is the typical case when we want to set up our circuit simulation for the transistor level, but we are not considering this one anymore because we are just simulating RC circuit. So let's put V sign here to run some AC analysis. So we can set AC magnitude as a 1. So here it says that it has a 1 volt, right? So 1 volt. But it doesn't mean that we are applying the physically 1 volt peak to peak or 1 volt RMS. It just means that it is a unitless signal. We are applying as a very, very small signal, like very tiny signal, unitless voltage. And we take VSS here. So we can call register. At this moment, I'm gonna set as a 1 mega ohm arbitrarily. And for the capacitor, we can call this way, cap here, right? That. So when you press R while doing move, then you can rotate by 90 degree. And when you press W, then you can call wire. Okay, now we saved it. And let's name this one as out. Okay, very simple RC circuit. Then we can go to this part to call ADEL. Okay. Let's with pre-running simulation environment. Okay, so for this analysis, let's first run AC simulation. Oh no, this is DC. AC simulation. We can set arbitrary 1 to just 1 gigahertz without thinking too much. Then we can run it. All right. Then we have results here. Here we have to set as a dB20 to look at our standard body plot. Then we have this output, right? So we can see that, all right, so when you press B, then you can call vertical marker that tracks it. Anyway, so when we take the DC magnitude of this kind of transfer function, it says that, okay, we have minus 600 pico dB. It's such a tiny negative value, right? So it's almost going to 0 dB. So when you go through more high frequency, then it becomes micro and milli. And now we are going to some value in single digit numbers. Anyway, at DC, as we expected, it goes to 0 dB, which is the magnitude of transfer function equal to 1. And when we want to do some calculation about the pole frequency, then which value should we take a look at? Anyway, so this one, when we want to call vertical line, you can press V. When we want to call the horizontal line, you can press H on the keyboard, H. Anyway, so I will try to match this value, this vertical y-axis, y value to some value that can predict pole frequency. Negative 3 dB, exactly. Thank you. When you double click this horizontal line, then we can set it, the number. Here we can set negative, let's see it, negative 3. Here, right? So we have, it says we have 158.649 kilohertz. And let's have a check whether this value matches to our expectation. I also prepared very simple Python script here. So first order RC low pass filter pole frequency is very simply like 1/2 pi RC, as we did during our slide. And this is very, very simple Python script. So I just called NumPy and matplotlib engineering formatter. And when we run 2 times pi, we set register value resistance as a 1 mega. So it has a 10 to the power of 6. And we set capacitor as a 1 to the power of minus 12, which is 1 picofarad. And when we run it, then it says pole frequency is 159.15 kilohertz, which is quite close to our simulation result here. It's very close to our simulation results, but this is strange, right? We are thinking of, we are controlling or managing the ideal components. There is no such a thing, a real transistor that has a non-ideality. So we are taking, okay, ideal resistor, we are taking ideal capacitor, but there is some discrepancy. What will be the reason? When we simulate ideal components, then it should not deviate from our theory, right? 158 kilohertz. This is a bit challenging. So I'll show you what is the core reason about this. Okay. So the next one we will simulate is a pole zero analysis. When we go to PZ here, we can set the output and the input about our pole zero analysis. For the positive output side, it should be out. For the negative output node, this is already assuming that if we are simulating our circuit as a differential output. For the differential amplifier output, where is it? Let's draw here. So plus, minus, minus, plus. For this kind of differential output, then we have to plot the output in differential mode such that V out P minus V out N. This should be the output. But in our case, we have only one output, which is a single-ended. So we don't need to. Where is up my annotation? Okay. Okay, right. Anyway, so we don't need to set this negative output to specific value. So in this case, we can set it as a VSS, which is ground. Here, and the input source, we can set this V sign here. And we are not sweeping any variables, so we can just press OK. All right. Then with this condition, we can just run the simulation. All right. Then again, we can go to this main form and go to PZ. Then we can plot poles and zeros. So we don't have any zeros in our circuit, so we can only look at poles only here. Then we can plot it. Now we see it. All right. So it says that negative 159 kilohertz. So this is okay. This is different from what we have seen here, AC analysis for plotting for pointing out minus 3 dB, 158 kilohertz. Well, what will be the real we have? We have these kind of different values that is happening. Any idea? Any guess? Okay, this is a bit tough. So the reason is that our magnitude response when we analyze this kind of burst of the low pass filter HS, when we take the magnitude, which is absolute value, it becomes 1 over, taking this real part and imaginary part. When we take S equal to J omega, then we can take square root and real part square and the imaginary part squared, such that it becomes square root 1 plus omega square times RC square. So we can plot this kind of thing at pole frequency to figure out if magnitude is really 3 dB, such that I set it here, 20 times numpy log 10 and 1 over square root 2. So here we have pole frequency, which is equal to, in angular frequency domain, which is equal to 1 over RC. When we take the square, then it becomes to 1. Such that its magnitude, it becomes 1 over square root 2. Then what will be the dB scale value of square root 2? Then it says actually, indeed, it's not exactly same as a minus 3 dB. It has these kind of fractional parts. Minus 3, 0.1, 0.2999, something. So let's try to plug in this value such that negative 3.010, let's say 0.103. Okay. Then we can double click here. So negative 3.0103. Then what is the value? So it says that it has a 159.03 kilohertz. Here, right? It's more closer to what we are looking at this frequency, right? 155 kilohertz. But still there is some discrepancy. There shouldn't be, right? So when we take point-wise plot, then we can see that, okay, there are some less samples that is simulated here. So this is also important when we analyze circuits. When we want to analyze our circuits really, really precisely. So when we take automatic spanning, then it just automatically sets the number of points. So we can control this number of points by specifically putting values such that when we put 30, then it means that we are putting or generating 30 samples per decade. So times 10, times 10, times 10. From 1 kilohertz to 10 kilohertz, we are sampling 30 points. So this is good enough, I hope. Let's run the simulation again. right? Then go to this one. Yeah, so now it goes to more closer to what we are thinking of the theoretical expectation. 159.16 kilohertz. This is very, very close to our expectation, right? 159.155 kilohertz. So remember, we just only estimated, the Laplace, how do I say, the clipped out the other fractional part. When we take the full fractional part of minus 3.01029999, then it will become more close to closer to 1 by kilohertz in the fractional part. All right, so this is it about this kind of whole zero analysis. I hope this can be helpful for your CAD exercise. I try to remove this annotation. So where is it? Okay, there it is. Yeah, clear. All right. So, we can maybe have a break for 10 minutes. At this point, you can still post questions to the Pressimo platform. So we have 10 minutes break until 9:35. All right, so we can continue the rest of the content today's lecture. So we will go through second order RC low pass filter, which is still very, very easy, but is a bit challenging than first order low pass filter. Okay, so we have a low pass filter. That's the same. The transfer function, what will be the transfer function? For here, right? R1, C1, R2, C2. What will be the transfer function? This is a bit challenging to, think about without any hand calculation. So in this case, voltage division is no longer that simple. What we have learned about voltage division, like principle of fundamentals, we can think about, okay, well, if we don't have capacitor here, C1, then it's easier, right? Then we can maybe have this much R1 plus R2, then we can divide voltage. But it is challenging for the circuit with the capacitor in between. So in this case, we have to go through nodal analysis for two nodes, like Vx and Vout. Again, this is based on very simple Kirchhoff's law. We can take R1 current is equal to C1 current plus R2 current. Here again, this is a mistake. I should have noticed I should note it as a small I. So here we are taking the difference, right, between the Vin and Vx, which is a voltage difference going through R1. So current through R1 is this here, Vin minus Vx over R1. For the current, small signal current going through this capacitor, it becomes SC1 times Vx, here, Vx. Vx minus ground. And for current going through R2, it's very simple again, right? Vx minus Vout over R2. And we have to go through also nodal analysis at Vout node. Then we have to think about, okay, what will be the current as we did for first order RC low pass filter. IR1 is equal to IC2. IR2 is equal to IC2. Then Vx minus Vout over R2 is again simply the same structure as this, as C2 times Vout. So if we do some math, some like rearranging this equation, we can do maybe this one. This one first will be easier. We are interested in the relationship between Vin and Vout. We don't want Vx. So we can just substitute Vx equal to something and then plug in back to the first equation. Then we get some mass. After some mass, you can do a hand calculation. Then there is Vin equal to Vout times this kind of second order system. right? 1 plus something times s squared. So going back to the transfer function, our original transfer function, then we can take, okay, if SHS is equal to V out over V in, then it becomes to 1 over, as I said, 1 plus something times s squared. So this is a second order system that you may recall back to our previous prerequisite courses. So we have omega 0 squared plus omega 0 over q times s plus s squared. Here we call omega 0 as a center frequency of our second order system, and we call q as a q factor. And those are system parameters. So here we can plug in the same equations to this case. Here I am just ignoring the numeric numerator factor, such that when we divide both of numerator and denominator by omega 0 squared, then we can make this constant part as a 1, and this one s squared becomes to s squared over omega 0 squared. Then our omega 0 is actually 1 over this value squared. Square root, sorry. And then it becomes to the unit of angular frequency, radian per second. And for Q factor, you can do the same math by plugging in this omega 0. Then you can get Q equal some square root R1C1, R2C2 over some values, R1C1, R1C2 plus R2C2. Okay, then let's talk about the loading effect. So what do you mean by loading effect? That is the thing. Okay, by looking at these system parameters, we can find that, well, this omega 0 has first part of low pass filter and second part of low pass filter. When we ignore R2C2, then we can easily predict, okay, we have omega 1 is equal to 1 over R1C1, as we did in previous slide. And the other part, when we ignore R1C1, then we can easily predict, okay, omega 2 is 1 over R2C2. Then all of those parameters are included into omega 0 equation, right? So when we multiply omega 1 and omega 2, and when we take the square root, then we get it. 1 over square root R1C1, R2C2. And the Q factor, we also have a similar situation, right? Here in the blue part, R1C1, and the green part, R2C2. But who are you? This one. This is all of a sudden it came. So anybody can predict or guess. What is this one coming from? I mean, this blue part we can easily predict. Green part we predict right here. Blue part and green part. Who are you? This one. It's just all of a sudden it just appeared. Based on what mechanism this one is coming? R1C2. Of course, there might be some possibility that I did some math mistake, but I double checked that my math is not incorrect. Any idea? It's a bit tough, right? So this is indeed because of loading effect. What it means by loading effect? So when we think about this R1C2, that looks like, okay, this C2 is having some relationship with R1, right? R1 and C2. So this means that, okay, this C2 part is influenced not only by R2 only, but also by R1. Both of R1 and R2 are influencing C2 because there is a connection anyway. So there is some current flowing through, as we did for the nodal analysis in previous slide. It generates some current. That current flowing into, okay, let's go back to our nodal analysis here, right? So for R1, it is equal to IC1 plus IR2, and IR2 is equal to IR1 minus IC2. So current flowing to R2 is actually influenced by originally R1. So R1 is in the end impacting C2 somehow. That is the result of how we see this R1 C2 term. So we can also think about it. Okay, maybe I don't want this kind of loading impact. I want to clearly describe my low-pass filter by R1 C1 only and R2 C2 only. In this case, we can put buffer in between, such that the buffer means that the gain of factor of 1 that buffers and isolate input and output. That is the purpose of buffer. For the second order system, then we have, okay, HS is like this, as we calculated, and we get omega 0 and Q. Then what will be the transfer function in this case? You don't need to think about the exact equation, but how can we calculate this HS? This one is more easier than calculation about this one, the upper one. Come on. It's not that difficult, I guess. I mean, based on what idea we can think about calculating this transfer function. Sorry? Sum of this part and this part. Oh, there was a very close, but in the end, instead of summing them out, but we can think about multiplying. Yes, thank you. We are doing multiplication because we did for the Laplace transform or transient response. In frequency domain, we have to multiply the transfer function to get the whole transfer function. So it is simply, okay, 1 over 1 plus SR1C1 times 1 plus SR2C2. So this part transfer function and this part transfer function, because we are isolating the first low pass filter and second low pass filter by the means of buffer. So this one is for isolation. C1 plus R2C2 times S, R1, R2, C1, C2 times S squared. So it goes to, okay, now we have some different parameters, the system parameters. Omega 0 is equal to 1 over square root R1 C1, R2 C2. It's the same, right? Omega 0. But for the Q factor, now it has square root R1 C1, R2 C2 over R1 C1 plus R2 C2. So there is no such a kind of R1 C2 term here. So now C2 cannot see R1 because it is isolated by buffer. So there is no loading impact. This is the ideal. So this is the reason why I put at the beginning of our previous lecture, we need some sort of buffer here, buffer for the microphone interface. We need a buffer to avoid loading impact, to isolate stages. MEMS microphone case, this is a mechanical electrical something component, and the anti-aliasing filter that we studied previously. And we can think about this case. Okay, for MEMS microphone, I don't want to drive. I don't want to be loaded by the filter because this can affect MEMS microphone operation or performance. On the other hand, for the anti-aliasing filter, I don't want to be affected by the MEMS. I want to precisely set the cutoff frequency for the anti-aliasing. For this purpose, buffer can be used to isolate two stages. And buffer plays a very, very important role in analog circuit design. Okay, then let's think about limitations of RC low-pass filter. So actually, after calculating this Q factor, actually there exists some maximum value. This is another question I would like to ask. If you graduate high school, then you can solve this. What will be the maximum value of this Q factor? Any idea? Mathematical calculation at high school level. Any try? This looks like a bit not typical way we do math and calculations in high school. So it may be confusing to think about what will be the equation and maximum value. So answer is this: inequality of arithmetic and geometric means. Anybody who didn't run this in high school? No, right? So we all know x plus y is larger than or equal to 2 times square root xy for positive or zero valued xy. So this happens, the minimum value happens when x equal to y. So we can apply this one, right? Because we have R1, C1, R2, C2, right? For the denominator part, we can apply this equation. Then the denominator's minimum value becomes now square root R1, C1, R2, C2, the minimum value. On the other hand, for the overall Q factor, because our denominator's minimum value is existing, then the maximum value also exists. So 0.5. Because we plug in this 2 times square root xy here. So it becomes 1/2. So our Q factor of this kind of RC low pass filter is limited by 0.5. What about this one? Will there existing any maximum value? Okay, good. Thank you. Thank you. Thank you. Right. Yes. Can you explain why?
How this divided a larger
Yes.
number.
Yes. Yes. Thank you. So because we have R1, C2, those are physical values in our world. Those are our positive values. So our denominator is slightly larger than 0.5 case. But it's definitely less than 0.5. Okay, so what I'm talking about and what I want to talk about is passive second order low pass filter, RC low pass filters are limited to Q factor less than 0.5 or equal to 0.5. This is the maximum. So when we set this kind of RC low pass filter with the buffer in between inserted, and we make R1 is equal to R2, C1 equal to C2, then its Q factor overall, because when we set this one, right, R1 equal to R2, C1 equal to C2, it is less than 0.5. Definitely even not close to 0.5 because we have larger value here, 3, and the square root 2. It becomes to square root 2/3. So when we look at AC plot, which is body plot of magnitude response and the amplitude response in time domain. So left one is frequency domain, the right one is time domain. For the unit step response, right? Unit step, remember? Unit step response, this one, 0 to 1. This is a unit step response. Then we can see it, okay, for the passive RC low pass filter, it has a Q factor equal to 0.5. And when we set Q factor equal to 0.707, then you probably have run what is called Butterworth filter. And it has something like a different shape, a bit more, standing up a little bit more in frequency domain. And for Q factor equal to 2, now it has some kind of gain picking, we call it. We call this phenomenon as a gain picking. And in time domain, right, then when we set Q factor equal to 2, then the gain picking causes this Q factor equal to 2 to have some leaning here when we apply the unit step response. For the passive RC, it has a slowly settling. For Butterworth filter, it also has a faster settling, it looks like. But in the end, it doesn't make significant difference. What I'm going to talk about is this. Let's say I want to maximize the passband bandwidth here, because in the high frequency, what we want to do for anti-aliasing filter, we want to filter out those unwanted signals, including noise and other things. Anyway, for let's say for 10 kilohertz, it doesn't make any difference that much. It's just a difference of Q factor. Then at the same time, I want to make our passband alive. Let's say for our microphone interface, I want to maximize our frequency band as much as possible. For this one, well, we have Q factor equal to 0.5. It has a slightly less bandwidth than this Butterworth case. So when we plug in the center frequency here, F0, to our second order system for Q factor equal to 0.700 Butterworth case, then we get exactly same value as F0. When we plug into 3 dB, then we find out, okay, for the frequency value to make sure magnitude is minus 3 dB, then it is 1 times F0. Of course, this is not exactly minus 3 dB, minus 3.010299 as we did. What about the other case, passive RC filter? For Q factor equal to 0.5, it has almost like 30% slower bandwidth than the Butterworth. For the Q factor equal to 2, then it has almost like 50% higher bandwidth compared to Butterworth. So in this case, okay, compared to passive RC, which is a maximum value of Q factor equal to 0.5, then its bandwidth for the Butterworth case, it has much wider bandwidth, 50% wider. For the Q factor equal to 2, it has almost like twice wide bandwidth compared to the passive RC case. Of course, at this case of Q factor equal to 2, that it causes a transient ringing. So it's that when we, for example, like when we shake our cell phone, by some means of where we are making the transient response, unit step response, then it is shaking, not shaking, for example, from here to like this, then it will be affected by mechanical force that can cause some unit step response. So in this case, its transient response is slowed down. It takes a longer time to settle down. So I want to maximize the passband bandwidth. In this case, at high frequencies, attenuation is similar across Q values. But for low frequency, we don't want signal attenuation. We want to maximize, we want to make our signals alive as much as possible. And at the same time, we want a faster response. So in the end, Butterworth for Q factor equal to 0.700 is often chosen for a balanced trade-off. And in general, Q factor less than 0.5 cannot build various other filter variants, such as like you probably have seen during your bachelor course, Butterworth, Chebyshev, elliptic, and Bessel filters, those having like very sharpy edges that goes to more ideal filter. We cannot build based on RC passive low pass filter because its Q factor is limited by 0.5. I will not go through too much details about theoretical analysis why Q factor less than 0.5 cannot build these kinds of filters. You can search more. Anyway, we need active filters. We cannot use just RC passive version of the filter. So I just searched by Wikipedia and found out this diagram. So there are various types of filters for fifth order filter response in linear scale. It's not log scale, it's not body plot, but it's a linear scale. So like Butterworth, it has like this shape, Chebyshev, type 1 and type 2. For type 1 Chebyshev, it has some fluctuation in passband. For type 2, it has some sort of fluctuation in stopband. And for elliptic, it has a very sharp edge. We cannot build all of these filters based on passive RC filter. And indeed, when we think about our system, so this kind of phenomenon, ringing phenomenon, is actually when we describe our second order system based on phase margin. So we call this kind of Q factor equal to 2 case. Okay, we have less phase margin when we design analog circuits. So when we think about the relationship between Q factor and phase margin, then we can plot this kind of graph. So the second order system, it has a zeta value, which is 1 over 2 times Q. Yeah, I will go through how to derive this complicated equation in next lecture. Anyway, let's assume that this is correct. Then phase margin value, which is defined as a arc tangent 2 times zeta, something on the denominator. And we can actually approximate this kind of complicated equation by easier format, which is phase margin can be approximated by 100 times zeta, and the zeta value is called a damping factor. When we study mechanical engineering course, then damping factor can be seen more often. So damping factor is defined by 1 over 2 times Q. So phase margin is actually approximated 1 over 50 until some value of damping factor equal to 0.7. And when we plug in Q factor equal to 0.707, which is Butterworth case, then we found out, okay, our phase margin criteria to build Butterworth filter is 65 degrees. So phase margin in some range of 65 to 70, it goes to Butterworth filter response. And this is the reason why a phase margin like larger than roughly 65 degrees is commonly chosen as a practical rule of thumb for designing analog circuits. So this is the end of our slide for lecture. So we will go through how to derive that phase margin equation and more going to deep inside of Laplace transform and feedback theory of second-order low-pass filter. Okay, so we can have a break for 10 minutes, and then we will probably go through the quiz. Thank you.